So yesterday evening I catted something up. And if this is somewhat working on the first try, I'm gonna do something incredibly stupid. Like, I don't know, post a video on next 1st of April about my company only producing Ducts or something. Let me check that. Okay, in terms of making that video, I think I got lucky here. This does, well, somehow work, but not the way I intended it. So basically what you're looking at is another, like, first prototype to the water vapor infusion. So last time we did discover that actually in the point where the water vapor is being infused in the airstream, the cooling quality has been really good with very low air pressure. So, and this is the very first shot at a conical water vapor distribution system, I guess you want to call it. And this basically combines two things, and maybe I'll put an overlay here from the CAD side of things. So basically we got shop air going on in here, and there are basically two circles in that part. The lower one I tried to design an air knife. There's a gap of 0.3 millimeters that shoots out shop air, and the idea is that this curvature here points that air directly to our meeting point just below the nozzle. What I try to do is redirect this air down here and then also draw a vacuum, and this is for the upper part. This is where my water infusion contraption comes in and puts water vapor in that upper ring. And because we want to draw a vacuum here, this should suck all of that down here in that stream. But let me hook on the air. Let me show you why this isn't working as intended. Okay, just having a look at the water part. Let me try to get this as low as possible. You can of course see this is the side where it gets like put in, and there is a direct stream going out of here because this basically has no resistance. And then there is another stream that basically bit of the air on both sides is going to follow around that path, hit in the back, and then create something like a swirl down there. If I don't move and breathe too much, you can actually see it. Okay, so far so good. If I ramp this up a bit more, you can see how much more turbulent this gets. And then if I'm going to put some shop air to the lower ring, so basically you can see my whole vacuum idea here isn't working. So apparently also most of the shop air, or at least part of it, is going upwards because I guess there's too much pressure here and the angle isn't sharp enough. And when I give this some more, you can see there's a clear indication that this is creating a positive pressure up here because it's blowing material out of here. So basically it feeds back into the box and creates a positive pressure. This is an incredible delicate part, and there's so much fluid dynamics going on. This is a single part you could write a thesis on. Everything has to work together. You see, I'm putting vapor in here. The distribution is not symmetrical. Like swirling around the air from the shop in here because it was the easiest way to go. And when I put my hand down here, I can see that basically everything is coming out this side, and this makes perfect sense after all. It comes here in a swirl, it has negative, negative, negative pressure, and once it comes up here, it starts to mix with this positive pressure from the inlet. And then basically the point where it exits the swirl is kind of here, and that's why I'm feeling the most air coming out of the system here. So I guess for today, I'm going to just quickly draw up a version 2 of that, put it on the printer, and then I'm gonna submit all the things I did want to do in the last episode in terms of printing speeds, etc. I have the air bearing glued back together, at least I hope so, we'll see. We're gonna run as long as this lasts. In case you didn't know, my name is Jan, I build stuff so you don't have to. Let's get on the machine.
Da 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 da.
Otherwise, we're gonna start where we left off last time, and then this cable thing broke. We're again going to print this cylinder in a bigger diameter with more infill, etc., so we don't have the layer time as a definite bottleneck here. We're gonna see if it is possible to extrude at 1500 millimeters a second. Still running 500k acceleration, 50 square corner velocity, 800. This is 1000, and by the way this sounds, I'm expecting something to break in any second, but I'm just gonna keep it running. So you may have seen these got ripped out again, at least it didn't break here. So I may have another chance. I'm gonna put it in and epoxy those in here. This is basically the last thing I can do before designing, printing, lapping and reassembling a new air bearing. I don't want to do that right now because this is epoxied in. This will take me half a day to perform, so let me do a last quick fix. At least in terms of this part, we got the results we wanted, because just to put this in perspective, this ran with the very low speeds at the beginning, maybe I think it was 14 minutes, and it is already 50 grams of material. And when I take my scale here, you can see it did complete the 1000, the 1100. Yeah, let's call it the 1100, depending on where you have a look at it. So my conclusion is we upped our layer times. This was what, like 5 seconds at the top where it started to go downhill. Cooling can't be the issue here. I had it at 1 bar, so throughout the print from, let's say, here on. So there is not the possibility of the filament being just blown away here. So I guess in this specific configuration I'm just not able to extrude past, let's say, 1100 millimeters a second. This is like the barrier we hit in all the other tests. Let's try a different filament. Alright, we got some new filament here. As you can see, this is a transparent purple. This has been sent over by Fiberlogy from Poland, and this is their high-speed PLA. And I've had this for quite some time and actually did some printing with it. And this is indeed one of the highest flowing materials I had ever on here, and this is also their claim. According to Dominic over there, they use a blend that is actually very close to the injection molding variant of PLA. Yeah, that comes with downsides but makes up for the best heat transfer inside the material, and that's what we're looking for in terms of flow. So the downside is you have to take that out of your extruder after you used it, basically. Because after it has been unwound, it becomes very brittle, at least in its natural form, not the print itself. Since taking out filament in and out from the extruders is kind of a pain for me, I decided to go with another filament, but let's just see if we can exceed 1100 millimeters a second with this filament and check our boundaries. Alright, let's do a filament swap together. Okay, I'm sure that all the strains are pulling at the same time. Gonna go 500 millimeters of filament with 100 cubes of flow. And we're going again with a Fiberlogy filament. I'm gonna get you in at like 700 or 800 millimeters a second. 1,000. So this is after like 15 minutes of high-speed printing. At the end it was like 1500 millimeters a second. We're going to talk about the print in a minute. The motor is at 110 degrees just a few minutes after finishing the print. And this is a great opportunity to speak about our today's video sponsor, which is PCBWay. Because what I find really interesting and impressive is how these things turn out. These are 13 gram weight nylon parts. I've shaved off gram after gram to make these as lightweight as possible in terms of accelerations, etc. And these hold up to this temperature. This shaft of the motor has the same temperature as we've recorded on top, transmitting the linear forces for 500k accelerations. I think this is just incredible. There's a link somewhere down in the video description where you get a discount on your first order there. They got a good website where you just upload your STL files, take whatever process you want to have, like sheet metal, 3D printing in all different kinds of flavors, etc. CNC milling, PCB layout and design. They have been of tremendous help going on with this machine, featuring a lot of parts here. So you should totally check that out. Thank you, PCBWay. And yeah, this is the print we've just finished. Won't you have a look at that? I don't even need my scale beneath it. This has finished all the way to the top. Yeah, so what does that mean for all of our stuff down here? Is it for the drain? Well, I guess no. We gained a lot of useful information, but this verified what we pretty much knew all along. Filament is going to be a huge factor in the speedboat race. Yeah, it seems like the brick wall we've been running into in the last test has been due to filament. This one is going all the way to the top, and truth be told, everything here 13, 14, 1500 millimeters a second does look impressively good. This features a bit of waviness, but then again, usually you don't see infill. I didn't want to put a solid layer on top at that speed. It is kind of a bummer for the catalog we've built so far. I mean, we can still draw a lot of conclusions from what we did early on, because in scale, everything should be applicable to this as well. But then again, I would have loved to have these tests done in this material in the first place. This, by the way, is King Rune PLA, which I used before. So basically the same material you see on this channel on this machine from the very first minute on. And this has been used by all the other speedrunners as well. Monica McWolf told me about it, and this is basically the same material, but we all know pigments do play a huge role in all of that, and black, we knew that seems to be one of the worst of them, but I had that on hand. Yeah, I get a lot of questions why I don't choose different filaments, or should we go to conductive ones or something, metal filled, because heat transfer will be better. Yeah, for sure. But there are two things that keep me from doing that. First of all, I have to buy 4 spools of all of that stuff to make it happen, or I have to re-spool it, which is a pain in the ass. The other thing is, I know how PLA works. PLA is very predictable and usable without a heated bed and a heated chamber and stuff like that. I want to take unknown out of the equations, and PLA is a known variable. For the future, I would like to test ABS and PETG, but both of them will have problems with warping and bad adhesion. So to keep my testing somewhat straight and linear, I stuck to PLA for now. I have something else in the pipeline, but I'm waiting for some emails on that note. Yeah, let me think about for a second what we're gonna do next. Alright, so should we move on with 2 different ducts to test for shop air? Or should we go ahead and test the next iteration of our water infusion? So my proposal is, shout it out now, and we're gonna do whatever you want. Oh yeah, perfect. Alright, I would have chosen these as well. Yeah, so with my testing or the needle approach on these shop air things, this is basically on the machine for quite some time. And I had 2 members from my Discord volunteering to design a new one. Actually, they came up to me and said, hey, I want to do this, and they got the CAD files to match this around, and let's call this one the Jason and this one the Lewis. So while this is being symmetrical and kind of open to feature a lot of air to the surrounding print, this should create a vortex around the nozzle and has like a very small point where you get a lot of airflow. So what I want to know is how anything compares to my needle setup, and if I'm running a system that is very bad in its performance and all of my findings here are just bad, I guess. So let me run with this filament a new reference print with the current setup. We're gonna have the same airflow, or let's say same pressure on all of these. And then we're gonna try to hook up these and run the same Benchy print again. Let's do that. Okay, starting with our Benchy reference print. This is with the needle setup. 3 minutes 20 again, looking kind of decent, does have its problems though. I got rid of some of those stringings in here, just gave it a quick with a blowtorch. I don't want to influence the looks of it by some stringing which is distracting us. The roof is dented in a bit, the chimney part looks really good. Outer walls are okayish, a few boogers here and there. Front half down here with the steepest overhang is beyond its cooling capabilities. Overhangs here are okayish but far away from crisp. Let's put on and let's start with the Lewis. Again here in a close-up, nozzle would be sitting right here in the middle. but a bigger part of that area is also being at least open to the duct. What I found when I had this connected with an air hose, most of that pressure is going out here. That is like following its natural momentum. This side here does get very low pressure. Let's just put it on the machine, run the same G-code with arguably the same pressure on the shop air side and compare the results. So this is a fit, even though it's very close. As you can see, there may be 1 millimeter of clearance here for the actual print. And this is almost touching there, so I have no idea how long that holds up due to thermal expansion and getting soft, etc. So let me try to print as long as it's working and let air get through it so it will be cooled. Let's go. So I'm reconsidering. Let's just not call that the Lewis, let's call that the eardrum buster. If you saw the camera shaking in the first minute, that is because I had to plug one of my ears with my finger. So yeah, but I think this is quite interesting. This is the new one, this is our reference. And what you can basically see is that in areas where the part is doing wide range of motion, decooling is actually pretty good. There is this one spot on top of here that is actually looking better on the eardrum buster as on my concept. But then you can see that the cooling flow all the way to the middle just beneath the nozzle is worse compared to my setup. You can see that directly here at the pillars. It is just moving over like a area of 10 by 10 or 12 by 12 millimeters. And right down in the middle there is just not too much of a cooling stream. You can see that in the chimney as well, if you have a look at them side by side. This one is crisp. This one was even soft 15 seconds after the print has finished. This is not great at cooling like the central piece of the print. But then again, the PID control of that hot end was like at 10, 15, 20% or something. So no issues there. I ran it all the way to 2.5 bars. There's less back pressure on this one as on my setup. And this results in also not having the top parts blowing down. So Lewis, thank you so much for designing this part. It fitted very good on the machine. There is an uneven amount of pressure to the front of the cooling duct, and we need more in the middle. So just running this one print isn't telling the whole story. But I think we do have some comparable data, and we know what to change in iteration 2. So I think we should install the JSON and see what this guy is up to. This is the duct JSON designed. Again, very, very close down here. I hope it will clear the print if like some filament sticking up there. Both of the designs are, for filming purposes, an order of magnitude better than mine is. You can clearly see what is happening, and also I can like film from the front. So let me run a Benchy. I have no idea if you could see that on the film, but the screw came loose and I was holding that motor in that direction for the rest of the print, and it became quite hot at the end. But I think you can see what it actually does to the print. I think the results are comparable. Let's go over to the bench. Same thing, this is our reference, this is the JSON. I think this here, what looks like a layer shift, this is the influence of the motor, and from that moment on I was pulling it to the side. But I think we can call that a comparable print. So in general terms this is looking pretty similar. I guess this even has a better front part. This like overhang does start to catch a bit earlier. This may be influenced because I couldn't run this all the way to the top with 2 bars before the PID control got bad, so maybe I was at 1.5 here or something. In overall terms it did very well. You can see for like cooling in central areas, this is a bit less effective than my needle setup. I can pretty much judge all of this by the duty cycle of my PID control. This is running full blast all the time. Lewis version was at, let's call it 15%, this was at around 40%. So we need more airflow at the nozzle, I guess, to, at least for a Benchy print. If we're printing bigger things, this is a whole different topic, but for Benchies with these pillars and this small footprint, and then especially the chimney, cooling in central areas does matter a lot. Overhangs here are, I would call it a bit better. So the conclusion is we don't need the needle setup, I guess. We can have something that is way easier to film around and work around. And with a bit of tweaking and maybe merging both of these, we could get to a similar good result that is way less aggressive on the duty cycle. So if you're interested in contributing as well, so both of these guys asked proactively if they could design a duct, and I gave them access to a folder in my Fusion. There's a link down there in the video description for my Discord. Way more information available than on these videos, even though they're that long. And while we're at it, so I've told you about this Patreon. If you want to support this project, feel free to have a look down there, and you can give me $1 or $2 to support all of this financially. Thank you. Also, sorry for my handwriting. This is version 2 of my water infusion thing. This has already been a great success in compared to the first one. So I fiddled a bit with different angles, etc. So this diameter has gotten bigger. Also the curvature is way steeper, and it seems to be creating more of a vacuum zone, and more of that stuff is actually going out of the nozzle. Let me switch it on. So this is water vapor only. And as you can see, or maybe not, most of it is now leaving downwards. There's again this bit of turbulence up there. And once we get shop air, you can see that most of the stuff is leaving downwards where we want to have it. I also put in 3 inlets for the shop air, so we don't have like one inlet and then just one positive pressure zone which is leaving like that. Now we have it at least distributed by 120 degrees, and this seems to be helping a lot. The cooling effect is clearly there, I can feel it on the hand. If this is enough to properly cool down a part, we have to see. The limitations I do have now is basically the amount of shop air I can add to the system. Maybe this works to this point. But still, at some point, it will create a positive feedback down here in the vapor generator. And therefore, we're kind of limited by our cooling capabilities. But this is a very low amount of push force downwards. But my hand gets pretty cold. So that's why I've already used the night to do a Mark III of this. This has, again, some slight variations in it. As you can see, it has grown bigger. Both the shop air as well as the vapor side has gotten bigger. I gave it some more restrictions here in the vapor inlet, so not all of it is going just out here. Also, again, I've upgraded this diameter by, I guess, 5 millimeters, put some more curvature in there. Let me put that on my test stand and see which one of those two we're gonna put on the machine, and then just see with some high-speed footage what it is actually doing there. Especially, like, I have to design it in a way that this is pretty much flat at the bottom. Especially for the first layers, this will just have 2 millimeters of clearance or something. I don't know if the air can escape down here, so we'll see about that. Let me put on MK3. So Mark III seems to be performing a bit less than its predecessor. The vapor side of things is pretty much unchanged. Let me adjust this to the point where most of it is still exiting south of the contraption. Now when I ramp in air, you can see that the vacuum effect isn't there anymore, so we got positive pressure out north. This is what we of course not want. So basically my brute force attempt here, without any like calculations or something, MK2 seems to be working the best. I have to derive what I changed, so maybe going back to the flow geometry of the air knife from Mark II, but extended. This has some convenient factors like I don't have to squish that tube so much for the inlet side. So there are a few things there that are positive here, but for the main function it's the Mark II. I'll try to get this on the machine. I already bought some ice. We can put in the vapor box to get this somewhere around freezing point, and then blow a rather constrained amount of shop air as a driver and the vapor as the catalyst for bringing out the energy out of the extrusion. Let me put that on the machine and see if everything fits. Within certain limitations, this serves its purpose. So it is blowing a vapor stream right down there. But I gotta run in for like a few minutes now, checking out a few things. And as you can see here, there are droplets building up everywhere. It got up to the extruder part. So basically I will be dealing with water vapor basically everywhere in the system. And if we continue to go down that route, I have to waterproof everything. I'm not even using like distilled water or something. This is just plain tap water. I can give it somewhere in the range of 0.5 bars of shop air pressure. Most of it, let's say 90%, is actually going down at the print. So for the very first test, let me try to get this all hooked up, see if the Z-axis is moving properly. Then just print a Benchy, but I'm gonna go with like 25% reference speed or something. I wanna have a print finished, see how the whole system reacts to it, what nozzle temperature says, so on and so on. And if we make that first print, this will be like a 5-minute Benchy or something. Then we'll ramp it up and see if we can like get something for our catalog there. I've also iced this baby up. When all this ice is gone, I'll take a temperature reading to get reliable data. Yeah, but first let me fuck up a very small thing, which leads to a 2.5 hour maintenance session. We'll be back. I think we're back up and running. Everything is homed. I checked the water temps. It is about 7 degrees in there. All the ice is gone. And I go ahead and we're gonna do the Benchy print as mentioned, somewhere in the 5-minute range. It will be incredibly difficult to film this. I try my very best and also try to obtain some high-speed footage. Let me see what I can do. Before we move on to the print, let's give you guys some parameters. So basically I gave this, I have no real idea what the pressure regulator says, but a fair amount of vapor. It is being limited by what the ultrasonic guy is doing down there. So I guess this was pretty much maxed out. And on the shop air part I had it at 0.5 bars, so pretty low. Everything with the Z-axis did work surprisingly well. Bed adhesion was not the best, but it held up, at least with these printing speeds. This was in total a 7-minute Benchy, but the first layers were very slow, so I had some time to dial everything in here and slowly ramp it up. PID control wasn't too concerned about it. As you can see, this line was pretty constant. So let's have a look at the print. Overall, a pretty decent Benchy. As I said, this would have been a 5-minute one if the reference speed was being held up through all of the print. I did ramp in the water vapor somewhere in here. Layer adhesion doesn't seem to be bothered by that. Also, the amount of water isn't that big in here. But as you can see, single point cooling as for the chimney is not there. I guess this will still be a thing that usual shop air cooling has to deliver, and I guess the water will take care of the majority of the print where everything has some time to actually evaporate the thing that has been sprayed on there. We're gonna print at higher speed, let's go somewhere 4 minutes, and I'll give it 1 bar of shop air cooling. Again, a very decent looking print. We might still have some headroom left. I was ramping in vapor again somewhere in here. This was looking pretty damn fine. And then I guess you saw in the high-speed footage how it loosened up. I've applied some new glue stick. Let's run it at Benchy pace, the reference pace, and see how this turns out. Again, 1 bar on shop air side and vapor turned all the way up. So let's note a few things. Single point cooling isn't quite there yet, but maybe we have to check where all this vapor is going. I do have the suspicion that the vapor is surrounding the part, but actually not touching the part. We have to think about that, and I got a strange theory in my mind about applying a voltage here, create an electric field, and therefore polarizing the vapor that's coming from the nozzle. But let's take this as a first result, and since this is a huge mess, I'm gonna do a last test for this episode, I guess. What I noticed is that the prints are looking decent by just using shop air with the air knife, and there is quite low resistance going in that contraption. So what I'm going to do now, run at reference speed and then give everything I got to the air knife. Let's see how that turns out. So there you have that. This is air knife. I can give it 2.5 bars of pressure. This is again reference speed 3 minutes 20. There are a few parts that look actually pretty good, like these overhangs and these outer walls. But then again, it starts to fail once layer times go down in the sub 1 second range. Especially the chimney was pretty much, was really limp when I first touched it. I could completely bend it with my hand. So I guess between this and the last episode, this is my full catalog of first prototypes you can build to have a quick peek in different methods of cooling. And yeah, we can draw a lot of things out of it that don't work. But it is our task, hopefully together, to find a solution for the future. It goes to show with all these testings that it won't be easy. I have one last thing in mind for water vapor cooling, and this will be the sort of spray mist things you can get for your CNC machine, which basically use the Venturi effect to draw from a tank and then shoot out basically water droplets, kind of fine-ish, over your part. I wanted to get around that and use this kind of an approach because there are droplets and there are droplets. And by using the ultrasonic one I have here, I got this very fine mist to use. That, on the other hand, is not easy to get into your cooling stream because I can't really get it inside the compressed air side, because it will then instantly drop out of the air because air can't contain it. I have to bring it in after expansion of the air, and that is my approach to get that as closest together as possible. By using these CNC spray mist devices, we will run into problems that droplet size is too big. But then on the other hand, we can see that right now with this kind of setup for larger print sizes, this works exceptionally well. This is at a few spots, this is our reference with needles, on par or better at cooling down the outer walls. But then again, for cooling down all those little details where the print is just moving on a very small envelope, I have not found anything that comes close to this performance here. Maybe the JSON approach is not bad either, but with all these benches I've printed, we run into the wall of physics. So I guess we have to take the route. This switching from black King Rune PLA to fibrology, high speed, transparent PLA made a huge difference in terms of how fast can we extrude. So I guess maybe it's time to have a deeper dive into materials. I have to write up some emails and see what I can get on the table. Another important outcome also is that apparently we need maybe 2 cooling systems. So the needle thing does work exceptionally well for all these pillars, etc., for small envelopes. But for bigger prints, we may need to have a whole sheet of cooling air run over the table, just like many other printers do. They have a part cooling fan and also they have like a chamber cooling or something. So I guess it will be some kind of a combination of all the things we have done so far. It will probably involve 2 kind of cooling medias. It will probably involve cooling down those medias. That will certainly help. Then again, doing this sub 1 minute will be a task. I guess this pretty much sums up my first iteration prototyping catalog for cooling. Again, link in the Discord, have a discussion with me and all the other guys, or do it in the comments. I'm very eager to hear what you do with all that kind of information. To end this video, my name is Jan. I build stuff so you don't have to. See you in the next one. Bye.